We're on section 3.5 and discussing direction of change. So if f prime of x is bigger than 0 on an interval, then f is increasing on that interval. If f prime of x is less than 0 on an interval, then f is decreasing on that interval. Let's look at the how it looks like on the graph. So the little arrow here shows the direction of the derivative, or it shows the tangent line, and so therefore it comes from the first derivative, right? We know that the slope of the tangent line comes from the first derivative. So when the first derivative is positive, this direction is upward, basically. And so and it stays positive. It just the function is gonna increase like that. But then if the first derivative here, I think first derivative is 0, so it's kind of it was kind of a top of the mountain kind of a deal. And then if the first derivative start becoming negative, the tangent line will look down, and then the function is going to decrease from there. And again, if the first derivative becomes positive, the same thing. So just those arrows will tell you which direction it's going. So the tangent line slope positive takes it up, slope negative takes it down. And that goes with the increasing, decreasing. When f prime is positive, it's increasing. F prime negative is decreasing. Now, looking at this, when you're looking at function y equal to f of x, and it's increasing, let's say between these 2 points, what it means for the derivative, let's say it's increasing between these 2 points, it means that the derivative, this is f prime of x in dark red, and orange is the f of x. F prime of x is supposed to be on the positive part of above the x-axis for that part, and then at here between these 2 points it's decreasing. F prime of x goes below the x-axis for that part, and then after that again it's increasing, it goes above. When it was decreasing down here, it was below. So that's how the relationship is, when f prime is going to go above or below when it's above or below x-axis, when f is increasing or decreasing. So now let's discuss concavity. Let f be a differentiable function and let a and b be an interval in the domain of f. F of x is concave up on a and b if the graph of f lies above the tangent line at every point in a and b. F of x is concave down on a and b if the graph of f lies below the tangent line at every point in a and b. Now, there's a relationship between concavity and the second derivative. If f double prime is bigger than 0 on a and b, then f is concave up on a and b. If f double prime is less than 0 on a and b, then f is concave down on a and b, concave upward and concave downward. The story of concavity also can be explained with the same animation. If the first derivative is getting becoming positive and more, becoming bigger and bigger, then the concavity is upward. So if the first derivative is increasing, concavity becomes upward. Look at this. And then if the first derivative starts decreasing, and you see the decrease, and you see a concavity downward, basically. So let's go back. It's around here that it starts decreasing, and so the concavity changes and it becomes downward. And then again at some point it becomes it starts increasing, and it becomes less and less negative, and it goes upward. And so concavity, when first derivative is positive, means the derivative of first derivative. When first derivative is increasing, means derivative of first derivative is positive. And when first derivative is decreasing, means derivative of first derivative is negative. So that's why the concavity up is the second derivative positive, concavity down is the second derivative negative. And the last thing about concavity is that actually there's a cute way of remembering concavity. If concavity is positive, means a positive smiley person, so concave up. If concavity is negative, then it means unhappy person, and concave downward. Why are we interested in increasing, decreasing, and concavity? Basically, up and down concavity. Many reasons. One of them is the shape of the graph. And so shape of the graph, if the function is increasing and the concavity is upward, basically it's going to look like that. If the concavity is downward and increasing, like that. And so if it's decreasing concavity up like this, decreasing concavity down like that. And so there are 4 pieces, and if you put the 4 pieces together, it would actually form the 4 pieces on the circle. So if you divide the circle into 4 pieces like that, these 4 pieces are like that. But then we wanted to put it on a table here and see that there are 4 options when you're drawing any interval that involves increasing, decreasing, and concavity. Example 1 on direction and concavity. Let f of x be x to the third minus x. On what interval is f increasing or / decreasing? So the first thing you want to do for this one is to take the first derivative. And first derivative is 3x squared minus 1. Set this equal to 0, and find where it's positive, where it is negative. Then the second part is on what intervals is f concave down or up. And then this one relates to second derivative. So how do we figure these things out? For the first one, when you set the 3x squared, so I'm solving part 1, 3x squared minus 1 equal to 0. The solution is going to be x equal to plus minus 1 over square root of 3. And then you have to draw the number line with negative 1 over square root of 3 and positive 1 over square root of 3. And then in here, you observe that this is a parabola, and it's going to be positive here, and it's going to be negative here. So the function is increasing negative infinity to negative 1 over square root of 3. And 1 over square root of 3 and infinity. And it's decreasing between on this interval, decreasing on 1 over square root of 3, negative 1 over square root of 3, and 1 over square root of 3. So that was the increasing, decreasing. How about the one with the concavity? Here, the second derivative only has 1, 0, x equal to 0. And that means that if I draw at 0, it's 0, and anything at 6x is positive after that, negative before that. So from 0 to infinity, concave up. From negative infinity to 0, concave down. Now let's look at this on the graph. So in here, I see that increasing, decreasing is happening. This orange line indicates the negative 1 over square root of 3, and that one positive 1 over square root of 3. And a function is increasing between negative infinity and negative square root of 3, and increasing from 1 over square root of 3 to infinity, and it's decreasing between negative 1 over square root of 3 to positive 1 over square root of 3. And then that's the other information. The concavity changes at 0. So concave down from 0 to infinity, negative infinity to 0, up from 0 to positive infinity. And these are the values again. Now, sketch the graph of a continuous function f satisfying the following. F prime of x is positive on the interval negative infinity to 2 and 7 to infinity. F prime is negative. F prime of x is negative on the interval 2 and 7. F double prime of 0, x is less than 0 on the interval negative infinity and 4.5. F double prime of x is bigger than 0 on the interval 4.5 and infinity. So now it's time to put all the data that we have about the function. So the important points are 2 and 7 and 4.5. So what is happening in here is that we know that between negative infinity and 2, function is increasing, and the concavity is less than f double prime less than 0 means downward. And so in here we're going to get increasing, and concavity downward looks like that. And then between 2 and 4.5, it's going to be decreasing, but concavity is downward. So that shape. And then I know between 4.5 and infinity, it's going to be concave up and decreasing. So like that. And I know that between 4.5 and 7, it's going to be increasing and concave up. Now, if I connect these together, looks like that. Does it always have to be connected? Sometimes they're, yes, and if they're part of the domain. There could be points missing from the domain though. So that's an approximate shape. Now, another question. Sketch the graph of a continuous function f satisfying the following. F prime is, again, I'm going to put annotated with the decreasing, increasing, decreasing. So f prime is increasing in here, decreasing, f is increasing here and here, decreasing in here because f prime is negative. And this time it's looking up over here, looking down over here. So when I draw the number line or and put in the important points 2, 4.5 and 7, and then look at the information given. I have to go up and the smiley face. So up and smiley face looks like that. And then between 2 and 4.5, it's down and still smiley face. So I have to go like that. And then between 4.5 and 7, it's down, looking down and increasing. And I'm sorry, decreasing. And so it looks like this. And then after 7, it's still looking down and it's increasing this time. So it looks like that. And so the next is, so that's how we basically find the graph of the function. Is just with the concavity and increasing, decreasing, you can graph a lot. More information needed to make basically this was giving any graph, but if you want a specific graph, more information is needed to do that. So I click here question 2. The cost of living continues to rise, but at a slower rate. Let f of t be the cost of living at time t. What does the quoted sentence say about f prime and f double prime? A, f prime is negative, f double prime is positive. B, f prime is negative, f double prime is positive. C, f prime is positive, f double prime is negative. D, f prime is positive and f double prime is positive. So take a moment. And now that you're back, let's solve this. And so the cost of living is rising. That means that the increasing. That means that f prime is positive, but at a slower rate. That means that it's just increasing, but it's sort of increasing less. That means f double prime is negative. So f prime is positive, f double prime is negative. That's C. I clear question 3. Which of B, C, and D is a possible graph of the derivative of the function A? So this is the function A. Notice function A is decreasing all the way to here, then it's increasing, and then it's just increasing from then on. So the derivative is negative over here, and then it's positive over there. And then the other part to notice is that concavity is upward over here up to here, and then it becomes downward a little bit, then upward again. So the graph of derivative should be basically increasing for a while, and then around somewhere here it starts decreasing and then starts increasing again. So let's see which one of these are going to work. Is this a good fit? B, it's just going, if I'm going, and these are all, when it's decreasing, it's below the x-axis, and increasing. Let's bring up the rest of them. That's C. And so let's go back to B. And then it's all negative over here, then it's all positive, and if you look at the it's actually decreasing around here, and then it's increasing from here to there, and maybe the concavity is matching right there. So how about this one? C. C is increasing, and then it changes the it goes it kind of where A is decreasing does not match where C is negative. C stops being negative earlier than A, so that actually is out. Here D is positive when A is decreasing, so that does not work. So between B, C, and D, or A itself, which one is the derivative of A? And I would say that B was the best fit there, because over here B is decreasing for a little bit, and you can see there's a little bit of concave down in there, and then it starts increasing, and it's where the concavity is positive. It hits the x-axis right when the function becomes increasing, and then it stays above the x-axis, and it changes concavity when I'm sorry, and it becomes decreasing when A changes concavity, and so on and so forth. So it follows A completely. So B is the answer.